Welcome to the second session. We're very happy to have Asilata Bapat telling us about triangulations, rigid motions, and applications to representation theory. Enjoy the course, and let's welcome Asilata.
Hey, thanks everyone. Thanks Masood and all the organizers. It's really nice to be here, and I want to say a little bit about this course. So as you can see, it has some words in it which are not traditionally related to representation theory. And in fact, Masood asked me to talk about some current research. So this is going to be kind of some work that I started a few years ago, but about a year ago, I came across some kind of connections to computer science, which show up in representation theory, and I would like to tell you about that. It's going to be necessarily rough around the edges because it's work in progress, and so I won't know all the proofs, and some of them will be left as exercises, and some of them are open problems. So I hope you can enjoy that. I mean, so for most, let's say for about half of this course, so maybe the first 3 days or something, I'm not really an expert on any of these topics. But anyway, I'd like you to enjoy that. So as always, if you have any questions, please ask. And another word of warning, it might, this whole course might vary in difficulty. So it'll start off quite elementary, and a lot of the things that we talk about will be very elementary, but then it might ramp up at the end. So don't be alarmed by that. And I'm always happy to talk to you if you need me. Okay. So I'm going to start with something very classical, which is triangulations of convex n-gons. And let's start drawing some pictures, because I think we all know what that is, but just to make sure. So here's a convex n-gon. So I'm going to be thinking about, what am I thinking about? So I'm thinking about convex, convex n-gons in the plane. In R2. Okay, so distinct points in R2 arranged in a convex arrangement. And what's a triangulation? Well, it's something like this. So I'm supposed to draw straight line edges joining pairs of points. Okay, and I keep drawing them until I have a maximal collection that doesn't cross itself. Okay, so so I'm looking at maximal collections of, I'll call them edges or diagonals. And by this I mean, of course, straight line. Okay, that don't cross. And of course, non-crossing means non-crossing in the interior. They can, of course, intersect at the edges. So as you can see, the convex hull edges will always be in any triangulation because you can always just throw them in. So really, we only care about the interior edges, and they might change. And so the first, well, there are many questions you can ask about this. Why is this relevant? But we'll get to that. But one question you can ask, of course, is if you fix a convex configuration of points, how many triangulations does it have? And probably many of you know the answer to this. And if you don't, it's a really nice exercise. So I'll leave that as an exercise. So here's a question. How many triangulations? Right, and then the second question. So this is going to be an exercise, of course, and it's a beautiful exercise. But the second question that I want to explore, especially later on, is what can you do if you remove the restriction that you have a convex n-gon. Okay, so that's where we're going eventually. So I'll write that as a question, but for now I won't say anything about it. So what if you don't have a convex arrangement? Okay, so let's start doing some basic combinatorial properties of these things. Again, much of this is probably not new, but just to orient ourselves. So here's a triangulation of 5 points. So there's a basic operation that triangulations support, which is called an edge flip. Okay, so I can look at one of these. The edges are either external or internal, so they're either on the convex hull or not. And if you have an edge that's not on the convex hull, maybe this one here, and if I delete it, then I can flip it. So what does that mean? Every single internal edge bounds 2 triangles. And if you take the union of those 2 triangles, you get a quadrilateral, convex quadrilateral. And a convex quadrilateral has 2 diagonals. So one of them was the edge that you just removed, and it has another one. So you can throw in the other one. So actually, let me go back and, oops. So this here is an edge flip. Okay, and this, just to spell out what this means, every internal edge in a triangulation, oops, has a unique flip, meaning if E is an edge inside a triangulation, so of course a triangulation is a set of edges, is internal, then there is, so you can remove it, and there's exactly one other thing you can add in. So there's exactly one other E prime, such that T, remove E, add E prime, is a triangulation. And you don't have, obviously, much of what I'm saying is you don't have to have points on R2. You can have points on other manifolds if you like. I mean, there are other things you can do, but for now, let's focus on R2. Okay. Great. So this maybe is not completely obvious, but again, left as an exercise. So let's think about how many, so again, we're doing basic properties. So how many edges are in a triangulation of n points, right? And how many edges, how many triangular faces? So first of all, okay, one other comment. The definition of a triangulation makes no reference to triangles. So one has to prove that if you have a triangulation, that you actually get triangular faces. Again, exercise. So, okay, but let's assume that for now. And then, so here's, and I'm going to do this in more detail than you might want, and it's because it's going to be relevant later. Okay, so here's something about the number of edges. In a triangulation. So how do you count something like this? Suppose you have, suppose we have a convex n-gon. I keep drawing pentagons because it's easy, but you know. And suppose we have a triangulation. Okay, so now let's count how many edges might be in such a thing. Does anyone know already how to do this? I'm sure there are many ways to do it. Okay, so I'll do one. So here's once again my pentagon. So notice that if I draw a triangulation in the plane, it's a planar graph. And so we have some tools to count edges and faces and vertices of a planar graph, namely the Euler characteristic or the Euler's formula. So remember Euler's formula. So we have n vertices. Suppose we have e edges. And f triangular faces. So I'm looking at the internal faces, not the external one. Then we have this formula n minus e plus f equals 1. So it's very, very classical. Okay, so that's good. And then, so we need something else to relate e and f to n, but we know that a triangle has 3 sides. So great, so we can do that. So each face has 3 edges. And if you, okay, so the number of edges is going to be 3 times e, but of course, minus something, blah, blah, blah. So what do we need? So we have 3 times e is counting how many edges each triangular face has going per face. Of course, this means you count most edges twice, because if each edge bounds 2 triangles, unless it's an edge on the outside. So 3f is 2e minus n, because there are n external edges. So now, I hope I got that right. I've made notes for myself just in case, because it's hard to do these things live. Yeah. Okay, so I have n minus e plus f equals 1. 3f is 2e minus n. So once again, this gives me, so this thing here gives me that 3f is 3 plus 3e minus 3n. And so that produces for me a formula for the number of edges. So 2e minus n equals 3 plus 3e minus 3n. And so let me know if I'm making an error, but I think if I did everything correctly, I should get e is 2n minus 3. Okay, and of course I can, this also gives me that f is what, n minus 2. Okay. So kind of an easy application of Euler's formula, but it's a nice count, and it's a nice way to prove the number of edges. I mean, you could, of course, think about other ways of proving that the number of edges is 2n minus 3. You could try some inductive proofs, etc. But the reason, again, why I'm doing this is because variations of this will show up throughout the course. Okay, so it's nice. It doesn't, the number of edges and the number of faces does not depend on the triangulation. It's always 2n minus 3, and the number of faces is always n minus 2. And then, and this makes sense because if you flip an edge, then the number of edges doesn't change. So you think if you can get from one triangulation to the other by flipping, the number of edges shouldn't change. In fact, it doesn't. And in fact, here's a statement, which again is an exercise. So what you can do with this whole setup is you can form a flip graph. So you can pick a triangulation of your choice, and you can start flipping internal edges. And if you take a triangulation and you flip an edge, you get another triangulation. So you make a graph whose vertices are the various possible triangulations, and you draw an edge if you can flip from one to the other. So here's an example. The flip graph, again for the pentagon. Once again, it's easy. Okay, so I can start at some point and start flipping. So maybe I flip this edge here. And the moment I do something like this, I connect them. Okay. Once again, now I flip the other edge. What did I just do? Okay, flip this one. And then once again, flip the other one, and then I'm back to where I started. I think, yep. So, so you could of course do this for any number of points, and a not particularly difficult exercise, but still I think fun, is to show that the flip graph is connected. So you can get from any triangulation to any other one just by performing a bunch of flips. So there's lots of work kind of that I'm not going to talk about in this class that's connected to this. For example, people have done a lot of work on computing the diameter of this flip graph. So, okay, so this graph is connected. So as you can see here, you can get from any triangulation to any other one using 2 steps. So there's a lot of work on computing the diameter of this flip graph. What's the minimum number of steps you need to get from one triangulation to the other? It turns out there's a nice paper by Slater, Tarjan, and Thurston, which talks about this in the context of like rotations of binary trees. It's really beautiful. So it turns out, binary trees are important data structures in computer science. And there's an operation called rotation on binary trees. And if you look at them the right way, it exactly corresponds to flipping in a convex triangulation. So it's important to know what the distance is between 2 binary trees if you want to get from one to the other by rotation. So there's a paper that kind of computes a bound on this diameter, and it uses hyperbolic geometry. So it's really nice. So I recommend you look at it if you like the stuff. Okay, but there's that. So I'll post printed notes, which will have all these references, so you don't have to write them down. And then the other nice connection is that you can not only can you form kind of a graph. So a graph is just kind of a one skeleton where you have vertices and edges. You can form a whole polytope out of this. So another thing that I won't talk about is the following. Don't even know if I should say, well, I'll just say, so in fact, the vertices of the flip graph can be realized as the vertices of a polytope called the associahedron. So you'll see a couple of exercises about this. Once again, kind of flipping in triangulations has various realizations. I just mentioned one, the rotation of binary trees. There's also kind of changing of parentheses as you write down an expression and write down various ways to parenthesize it. So it's kind of the associativity relation shows up exactly like this. So there's an exercise about this. You can have fun with that. And in fact, that's where the name comes from. So you can kind of flipping an edge in a triangulation corresponds to kind of changing parentheses in an associativity relation. So that's nice. And you can form a polytope out of this. So there's work on this that you can go look up. But I won't talk about this any further, even though it's cool. Okay, so maybe just to finish up with kind of triangulations of convex points, what I want to talk about is a little bit of kind of classical applications of this stuff in representation theory or sort of more algebraic incarnations of this. So here's an application. So, okay, all of this, there was so far sort of no representation theory, but here is an application to the cluster algebra of type A. So I'll say a bit more about this. So like many of the things that I'm going to talk about in this class, I won't necessarily give you formal definitions of things, but I'll try to give you a flavor. So here's a flavor. So what I'm going to do, once again, I'll start off with a convex arrangement of endpoints, and I'll tell you a mutation rule. Okay, so here's, so once again, let's start with a triangulation. And I'll give you an algebraic incarnation of kind of the operation of flipping here. Sorry, 1 second. So for convenience, I'm going to label the vertices of the triangulation. I'll just label them in order. Okay. And I have certain edges in the triangulation, so I'll look at formal variables. So I'm just going to throw in variables xij every time there is an edge ij. Okay, so the order between I and j doesn't matter. Whenever I is connected to j, well, is an edge in the chosen triangulation. Okay, so in this case, I have, so of course I always have the convex hull edges, x12, x23. I mean, I'm even going to stop writing them probably. Okay, but then the more relevant ones are x25 and x24. And just for the sake of notation, it doesn't matter so much, but given, so if T is my triangulation, let me call this set CT, okay? So now, this was my starting point. And I'm going to think about a flip. Okay, that's all I seem to be doing right now. So I'll flip my favorite internal edge, maybe 2, 5. Okay. And what I want to do is I want to, I'm going to give you an algebraic operation to do every time I perform a flip. Okay. So here's what I'm going to do. So once again, remember, a flip means you have an internal edge which bounds 2 triangles. The triangles form a quadrilateral, and I'm taking one of the diagonals, I'm removing it and replacing it with the other. Okay. So what I'm going to do is I have the set CT. Okay. As described above. And okay, I mean, flipping is a reversible process, but at the moment I'm going to give you a recipe which produces CT prime. Okay, so this is T and this is T prime. And here's the recipe. So I look at the quadrilateral that bounds the edge that I'm flipping, x2, well, 2,5 or x25 is the variable. And the only thing that should change in CT prime is that x25 should be replaced by something else, because everything else is the same, right? So instead of x25, I should throw in an x14, but I'm going to give you a relationship between them. So here's, so CT prime is going to be CT minus x15, sorry, what's that, x25. But I throw in x14 where, and I'll rewrite this I'll write this in a minute, 1 second. I just want to show you 1, 2, 4, 5. So the algebraic relation that I impose here is that x14 times x25 is x12 x45 plus x24 x15. Okay, so the product of the diagonals is the sum of the products of the opposite sides. And this is probably a familiar relation. It's called the Ptolemy relation, or at least I call it, most people I think call it the Ptolemy relation. People know where that word comes from, right? No? It's okay, so if you have this is classical Euclidean geometry. So if you have a quadrilateral that's inscribed in a circle, the edge lengths of that quadrilateral satisfy exactly this relation. And this was, I guess, Ptolemy's theorem. So that's why it's called the Ptolemy relation. Okay, so at the moment, I don't have any cyclic quadrilaterals or anything. It's just purely algebraic formalism. But the relation that I impose is that x14 times x25 is x12 x45 plus x24 x15. And therefore, this tells me how to compute x14. Okay, so x14 is the quotient of the right-hand side by x25. So I can now start playing a game, which is that I start off with a triangulation of my choice. I pick an edge of my choice, I flip it, and I create a new set of edges, and therefore a new set of variables. And I can, of course, keep going. So I can kind of keep going and come back. And of course, the question to ask is, what happens when I come back? If I start off with this triangulation, if I walk around my flip graph, applying this algebraic operation each time, I'm going to come back with a set of variables once I complete a cycle. And so the amazing theorem is that actually you get back exactly what you started with. So let me write that. Is there a question? Oh. No, yeah, the question was, is there any difference between 1,4 and 4,1? There's no difference. Yeah, x14 is x41. Okay, so theorem. If you, if you perform this operation in any cycle, of the flip graph, the set T, so maybe I'll say you come back to the original set. So of course, what I mean by this is if I start at T, and if I go around any cycle, I come back to CT. And this, of course, you could do this at any vertex. So this is, I find this kind of remarkable. I mean, I don't know a proof of this, like just by looking at what I'm about to give you a proof in a moment, but sort of directly, I don't think I really know how to prove this. So let me just say a bit of terminology. This operation here is called mutation, going from CT to CT prime. And by the way, I defined it as a one-way process, but it is of course reversible, because if the relation is symmetric in x1, 4 and x2, 5, so I can go back the same way. So I'll draw a double arrow here, and this is called mutation. At, let's say, at the edge 2, 5 or 1, 4, depending on your perspective. And these subsets of variables here are called clusters. So this is Chris.
So is it like the CT prime seems like it's clearly reversible, like just as the variables that are changing, nothing exotic is happening. So is it that when you go around the cycle, you're not imposing any additional relations on the original variable?
I mean, it's conceivable to me that if you go around a cycle, it could happen that whatever x25 you come up with is no longer equal to the x25 that you started with, assuming, of course, that you're imposing no other relations, just formally. But in fact, it does end up being equal. Okay. So okay, so I'm just going to leave it there for the moment. I'll come back to this in a minute, but I just want to make a remark here. So the sort of mutation operation that I've described in terms of a Ptolemy relation is a special case of a much more general thing you can do, which is the construction of something called a cluster algebra. So a cluster algebra has exactly the same sort of flavor. You start off with some basic set of, let's say, formal variables, and you have an external gadget that gives you a mutation rule. So in this case, the mutation rule is specified by a triangulation. It need not always be. There's often a quiver in the background that specifies the mutation rule, so you can do that, and then you can start off with your cluster. You can mutate. You get another cluster. You keep doing this, and you look at the algebra that's generated by all of the variables that you get in all of your clusters, and so that forms a cluster algebra, and then the data of like sort of each set. Each cluster is part of the generating data. So you can, and so if you do this, so in this particular case, it turns out that if you apply mutations, you just get finitely many clusters, and that's not always going to happen if your mutation rule is sufficiently complicated. In fact, getting finitely many clusters is quite a special phenomenon. So this is secretly, all of this is secretly alluding to the fact that. So actually, maybe I'll write a full remark. So this is a special instance of a more general construction. Called a cluster algebra. And the operation that I mentioned to you here is saying that the cluster algebra coming from triangulations of convex n-gons is of finite type, meaning it has finitely many clusters. And I've given you references in the printed notes, so you can, of course, have fun with looking up other cluster algebras. Okay, I should think about how much time I have, because I haven't really been looking. Okay, it's fine.
So, let's see if I understand what you do. Like, when you apply this map, you're getting a new set, but you can write the elements of the new set in terms of the previous set as rational functions.
Yeah, exactly.
And then you repeat and you get more complicated rational functions. And then when you do a loop, you get a super complicated rational function in the original variables, but they somehow cancel and you just get the excess.
Yeah, so the comment, exactly. So the comment was that if you keep applying this process, you can, every subsequent cluster can be written in terms of the original set of variables as a rational function. And then if you do this enough times, everything simplifies to get back what you started with. So that's the exactly. So that's the non-trivial, to me, non-trivial part of this. Yeah, that's fine. Yeah. And of course, like doing this for n equals 5 is in your exercise sheet. So I hope you do that and have fun with it, because you can do this by yourself. Okay, so I mentioned that I'm going to give you some sort of proof or some sort of idea of proof of this just in this instance. And so maybe I'll say like another class. I mean, well, yeah, this is kind of classical at this point. Another classical thing that's connected to just plain old triangulations of convex n-gons and flips in them, and also connected to this cluster algebra. So here's something geometric. And so we move to the Grassmannian. I want. So again, stop me if any of this is new, but maybe it's not, we'll see. So again, just to remind you, the Grassmannian, and I'm not going to worry about what field I'm over, some field, fix a field, okay? So I'm going to be looking at a fixed vector space of dimension n over my chosen field. So just k to the n, where k is a fixed field. And what is the Grassmannian? The Grassmannian is a space that parameterizes m-dimensional subspaces of k to the n. Okay, so it's it's a topological space. It's an algebraic variety, if you like. I mean, there are many ways to look at it, but ultimately, a point in the Grassmannian, GRMN, is going to correspond to a vector subspace of your fixed k to the n that has dimension m. And so eventually, I'm going to focus on the Grassmannian of two planes, so GR2n. Okay, but for now, let me just write things more generally. So if I, again, this might be something that you've done many times, but how do you write down a point of the Grassmannian, right? So I need to give you an m-dimensional subspace of k to the n. That means m linearly independent vectors. So a point in this space here is represented by m linearly independent vectors such that, so V1 through Vm, such that this set is independent. And I'm working very concretely with like coordinates. I mean, I have k to the n here, so I may as well write each vi in coordinates. And if I do that, I'll get a big matrix. Okay, so I'll do that. And which way does my matrix go here? Actually, let me check. Okay, so I'm thinking of a matrix like this. Doesn't really matter, but yeah, this way. So as written, it's n by m. Okay, but of course, this is not like a unique specification because each vector space has many bases. And so I can change bases and I will still get the same point in the Grassmannian. So how do I know if I have the same point? Well, I have the same point if and only if I have changed bases of the same vector space. So, exercise again. So if you have, okay, show that matrices as above, H1 and H2. Oh, and sorry, one remark I should make. It's not just any old n by m matrix, right? It's an n by m matrix of rank m. So that's important. Okay, so if I have two n by m matrices of rank m, and I want to know whether or not they give me the same point in the Grassmannian, well, they show that these two give the same point. If and only if one is a change of basis of the other, and I can write that by saying there is some matrix A in GLM such that H2 is H1 times A. Okay. Okay, and so just for convenience, since I'm only going to be looking at GR2M for the rest of the story, let me move to that case. So let me make M equals 2. So now okay, it doesn't matter, but just for convenience, okay. So, okay, if you have something like this, if you have a matrix of n by m matrix of rank m, what does that mean? It means, how do you detect whether a matrix has rank m? You look at its various n by m minors, and you compute the determinant and see if it's at least one of them is non-zero. That's how you figure out the rank. So here's so I'm looking at n by 2 matrices, and this has rank 2 if and only if some 2 by 2 minor has non-zero determinant. Okay, but of course we just discussed that two matrices could have could represent the same point in the Grassmannian, and what happens to 2 by 2 determinants if I multiply a matrix on the right by a 2 by 2 matrix? Its determinants multiply, and so they just get scaled. Okay, so, but in fact, if A is any 2 by 2 invertible matrix, then the determinants of the 2 by 2 minors of HA are just the same as the previous minors, previous determinants times the determinant of A. the same as before, but scaled by det A. Okay, so this, all of this is to simply motivate something that you've probably seen before, namely the Plücke coordinates. So this motivates and this is simply saying, look, I mean, I'm looking at my n by 2 matrices, but instead, let me simply just look at all of the 2 by 2 minors, all of the possible 2 by 2 minors of these n by 2 matrices, okay? But I'm going to do them, look at them up to scaling, because if, of course, if I multiply H by some A, then the minors get scaled, okay? So the Plücke coordinates are as follows. So if H, and I'll write it like this. So if H is a point in the Grassmannian, meaning H represents, H, the matrix represents a point in the Grassmannian, but of course the equivalence class being any other matrices that represent the same point, then the Plücke coordinates are simply the collection of all possible 2 by 2 determinants. So determinant of H ij, okay, where something like this is just the ith and the jth row. And then I'm looking at all of them up to scaling, so I should think of these as homogeneous coordinates. Okay, so these live inside some projective space. In particular, P n choose 2 minus 1. Okay, so they're all of these various ij minors up to scaling. And this gives me, in fact, a map. So this produces and you could have done this, of course, for any m, not just m equals 2, but and in fact, it's not too hard to show that this is an embedding. And so you can, again, we'll leave that as an exercise. This is called the Plücke map. And in fact, it's an algebraic embedding. So it realizes the Grassmannian as an algebraic subvariety of a big projective space. Okay. So now this gives me kind of coordinates, homogeneous coordinates on the Grassmannian, right? So this embedding gives, sorry. Homogeneous coordinates on GR to N, namely Pij of a point is precisely this determinant. The determinant that I wrote down before, and I have 2 minutes, so I'll say the last thing and then I'll stop. The only thing I want to say beyond this point, and you, again, there are some exercises that talk about this, is that these Plücke coordinates, these homogeneous coordinates, satisfy exactly the same relation that I had written down earlier. So if I kind of think about a convex n-gon like this, and if I label it clockwise, if I like around kind of around the n-gon, and if I choose any convex quadrilateral here, okay, so if ABCD is a convex quadrilateral in the picture on the left, then in fact, the previous relation holds. So P A, B, C, D. Okay, PAC, PBD equals PAB, PCD plus PAD, PBC. And this is something you can, this is something about determinants of a 2x4 matrix, 4x2 matrix. This you can check by hand. And this is true for every single every 4 coordinates that you choose. Okay, so this, in fact, the only thing I want to say about this is that the homogeneous coordinate ring of the Grassmannian is actually giving you kind of a concrete realization of the algebra that I showed you previously. And so this, in retrospect, gives you a proof, I think, that the cluster algebra that I showed you is a finite type. So here it is. I mean, this is what it looks like. Okay, I'll stop here. Any questions from Hawaii?
You hear that?
I heard something, but not the question. Should I?
Question. So at the beginning of the lecture, you mentioned the Euler formula like E minus. Could you scroll up to that?
Let's see. Is it this one?
The N minus E plus F is 1. Shouldn't be 2?
Yeah. Thank you. So yes and no. I mean, it's 2 if I include the outside infinite face. So there's, you can, so that you can think of the face on the outside.
Okay.
If you count that as a face, then you add 1 to both sides, and that's because the Euler characteristic of a 2 sphere is 2 is a sphere is 2. But if you remove that outside face, then you subtract a 1 from both sides, and then you get 1.
Okay. Thank you. Mhm.
I think there's no more questions here.
Okay, thanks.
Right, thank you, Asilata.